All right, so we are going to talk about Newton's third law. For every force, there is an equal and opposite reaction force. So let's get ready. So things to know. A force is always part of a mutual action that involves another force. So on our paper, we're going to write some things down. So the first thing we're going to write down is that for every action, there is an equal and opposite reaction. It can also be written as for every action force, because these are all about forces, there is an equal and opposite reaction force, okay? Because that's what we're talking about again. We're talking about forces in this unit. So let's think about this, okay? What is a force? We talked about that earlier. But in the simplest sense, a force is simply a push or a pull. So on your paper, where it says what is a force, fill in, it is a push or a pull. Now, a mutual action is an interaction between one thing and another, and that's what we're going to be talking about. So when I push on the wall, or when you push on the wall, guess what? The wall also pushes back on you, okay? The interaction that drives the nail is the same one that halts the hammer. So, yeah, the hammer is hitting the nail down, but guess what? The nail is hitting the hammer up. If it didn't, the hammer would just continue to go down, okay? But it doesn't, it stops, all right? And it stops because of that action-reaction pair. So again, Newton's third law states whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. Those forces are equal, they're simply in opposite directions. Newton's third law describes the relationship between two forces in an interaction. All right, one force is called the action force, and the other force is called the reaction force. Neither of the force can exist without the other. So in order for there to be an action, there has to be a reaction. In order for there to be a reaction, there has to be an action. They're equal in strength and opposite in direction, and they occur simultaneously. What does that mean? This means they occur at the same exact instant in time. So it's not this happens first, then that happens second. They happen at the same time. That's the part that can get people a little bit confused. When I push on the wall, it's pushing back on me immediately. Okay, if I push on a chair, the chair pushes back on me. It's not I push on the chair and the chair moves. That's not an action-reaction pair. I push on the chair and I feel the chair also pushing back on me with that same amount of force. All right, Newton's third law is often stated, to every action there is always an equal opposing reaction. And again, there's action and reaction, but it doesn't actually matter which one we call the action, which one we call the reaction. They're occurring simultaneously. For every interaction, we've got them always occurring in pairs. So I'm pushing against the floor as I stand on it. Guess what? The floor is pushing against me at the exact same instant in time, which is why I'm not falling. The tires of the car interact with the road to produce the car's motion. So the tires push against the road. Guess what? The road's pushing against the tires simultaneously. When I'm swimming, I push the water backward. The water pushes me forward at the exact same instant in time. That's why I can move forward when I'm in the water. The interactions in these examples depend on friction, okay? If a person trying to walk on ice where friction's minimal, they may not be able to exert an action force against the ice. They might just be standing there slipping and not going anywhere. Without the action force, there cannot be a reaction force, and therefore there's no resulting forward motion. So again, if you're on super slippery ice, you might just be standing there moving your feet and not going anywhere. You need that friction. In this case, we've got action-reaction. The girl pushes the boat backward. The boat pushes the girl forward. So yeah, she goes forward, but that boat's going backward. So when you're trying to identify a pair of action-reaction forces, you should first identify the interacting objects, and then just say if the action A is on B, then the reaction, just flip it around. B is on A. And you just flip it around a little bit. So here we go. We've got the tire pushes on the road. Guess what? The road pushes on the tire. All right, so the reaction is the road pushes the tire. Here we've got the action, the earth pulls the ball down. Guess what? The ball is pulling the earth up as well. Over here we've got the action, the rocket pushes the gas backwards. Guess what? The gas is pushing the rocket forwards. What the heck? I don't know why it's not advancing, but we'll figure it out. There we go. All right. When a cannon is fired, there's an interaction between the cannon and the cannonball. The force the cannon exerts on the ball is exactly equal and opposite to the force the ball exerts on the cannon, which is why the cannon kicks backwards. So the cannon pushes the ball forward, the ball pushes the cannon backward. But the cannon doesn't move a whole lot. Why? We need to consider the masses. Okay? We need to consider the masses. Oh, if you didn't write down these reactions back here, they were on your paper, okay? Also the water ones, I forgot about those ones. So if you didn't write those down, these ones, they're in your paper as well. So you need to go back, pause the video here, write those ones down, pause the video here, write these ones down. All right, so again, we've got this cannon pushing the ball forward and then the ball pushing the cannon backward. But the cannon doesn't really go backward nearly as much as the ball goes forward, and that is due to the difference in mass, okay? The forces are equal, so let's just make the number 10, okay? So 10, okay? They both have an equal amount of force, but we're gonna make the acceleration big, so make the acceleration 5. The mass is small. I know it could have made it bigger between the two, but this will get our point across. So we're accelerating at 5 here. The cannonball accelerator has an acceleration of 5. Over here, we'll make the mass of the cannon really big, like 10, and that means the acceleration is only 1, okay? So the cannon accelerates much less. Why? Because its mass was quite a bit more, okay? And that's the way that you can have this action-reaction pair where the force is the same, but the accelerations are significantly different. It's because of a significant difference in the mass. All right. On your paper on the back, when the cannon is fired, the cannon exerts a force on the ball, and the ball exerts a force on the cannon. Why does the cannonball fly a long distance? The cannon only moves slightly. The cannon is much more massive, therefore it does not have as big of an acceleration. All right, last part on the back. We're getting towards the last part. The birds and the airplanes fly because of action-reaction. When a bird is soaring, the shape of its wings deflects air downward. So the air gets deflected downward, the air in turn pushes upward on the bird. So the bird's wings push down on the air. Reaction, the air pushes up on the bird's wings. Oh, look at this. Guess what? If you hit the wall, it's hitting you back just as hard. Okay? Honestly, the wall hit my hand and I sprained my wrist. All right, here we go. If a sheet of paper is held in midair, why the heavyweight champion of the world could not strike it with a force of 200 newtons or 45 pounds. Why? If the paper, why is this part? The paper is not capable of a reaction force of 200 newtons, and you cannot have an action without a reaction because the paper can't accelerate fast enough to get a 200 newton force. So it's just going to move, and you might try to hit it hard, but it's going to move and you're not going to be able to apply that big of a force to it. Now you put the paper against a wall, go for it. You can apply 45 pounds worth of force and hurt your hand, so please do not do that. Okay? So on your paper, fill those in. The paper is not capable of exerting a reaction force of 200 newtons, and you cannot have an action force without a reaction force. And then you can fill that part in for the last part. All right, so your assignment now is to complete the third law worksheet.